Hi everybody, in this video we are going to discuss phasor diagrams. Suppose we have the following circuit in which we have two current sources, one over here and one over there. And this one has an amplitude of 2 amps and this one has an amplitude of 3 amps. And they both supply a current into this resistor. Well, you could say, well, the total current which is flowing to this resistor is 2 amps plus 3 amps is 5 amps. But that is not the case. And why is it not the case? Because this current has a phase angle of minus pi over 4 degrees, and this current has a phase angle of pi over 2 degrees, which is not the same. So these phases are not equal, and that's why we may not calculate the total current by adding simply these two current values, I should say. Well, how should we do it? Well, let's look to this situation in which we have a sine or either a cosine. Sine starts over here. We could also define it as a cosine starting over there. What do we know of this cosine? Well, it has a phase angle of minus 1/3 of pi because it starts somewhat later, and it also has a certain period time. Well, let's have a look. The period time is about 10 milliseconds, which is 0.01 seconds, and then we can calculate the radiant frequency from this period by um, calculating 2 pi over t, which is equal to 2 pi times f, which is 2 times pi over the 10 milliseconds, which we have calculated here, which gives us an angular frequency of 628 radians per second. So now we can define this waveform as a cosine with a top value of 10 volt, which can be seen over here, times the cosine of omega times t, omega is 628 radians per second, plus my phase angle, which is minus 1/3 times pi, which is standing over here. This is in the time domain. Now we can express this figure also as a phasor. And this is the way we do it. We draw two axes, a horizontal axis over here and a vertical axis over here. In this phasor diagram, we draw an arrow, which we call a phasor with a certain length, and this length is 10 volt, which is the maximum amplitude of this voltage over here. This phasor turns with a speed which is equal to omega, 628 radians per second. But that is not that interesting. What is interesting is at t is 0, here t is 0, it makes an angle of minus 1/3 times pi with a horizontal axis. And that is this angle. And why is it this angle? Because we defined this as a positive angle. So this is plus 90 degrees or plus pi over 2 radians, and this is minus 90 degrees, so minus pi over 2 radians. So minus 1/3 pi is somewhat over here, which is minus 60 degrees. Well, this is my phasor. So knowing that, we can redefine this problem which we had to a problem with two phasors, and then add up the phasors and then look to the combined amplitude of the new current which we have, the new amplitude and the new phase angle of this current with the x-axis. Well, let's do it. We have two currents which we defined over here. This one has an amplitude of 2, it is a current 2 amps and a phase angle of minus pi over 4 degrees, which is minus 45 degrees. This current has an amplitude of 3 amps and a phase angle of pi over 2 radians, which is 90 degrees. So we put them in a phasor diagram. This is my phasor for this expression, an amplitude of 3 and a phase angle of plus 90 degrees or plus pi over 2 radians. The other phasor is drawn over here, a length of 2 amps and a phase angle of minus pi over 4 or minus 45 degrees. Now we can calculate the combined current by adding up these vectors, and we do that by splitting these vectors up in a horizontal part and a vertical part, and then we add up the horizontal parts and we add up the vertical parts, and based on these horizontal parts and the vertical parts we can calculate the new length and angle of that combined vector. Well, let's do it. We start with the red vector, which is drawn over here, which has an amplitude of 2. The horizontal part, xi1, is equal to 2 times the cosine of this angle minus pi over 4. So it's 2 times the cosine sine of minus pi over 4, which is the square root of 2. The vertical part, yi1, is 2 times the sine of this angle. So 2 times the sine of minus pi over 4, which is minus the square root of 2. So that is the division of this phasor and horizontal part and the vertical part. Now let's do the same with the blue vector, which is drawn over here. And of course we can see that this vector is already only on the vertical axis, so it has a horizontal part of 0. Okay, but we can also calculate the vertical part, and of course we can also see that because it has the length of 3 and it has the phase angle of pi over 2 radians. Now we can add up both the horizontal parts and the vertical parts. So the horizontal parts together are this part, square root of 2, plus that part, which is 0. So the combination of the horizontal parts is the square root of 2. The sum of the vertical parts is the summation of this part, which is 3, and that part, which is minus the square root of 2, which is about 1.6. So the combined vector drawn over here has a horizontal part of square root of 2, and it has a vertical part of 1.6. Now we can calculate the complete length of this vector by using Pythagoras' theorem, and it says that the length of this vector is the horizontal part squared plus the vertical part squared, and then taking the square root out of it. So it's this parameter squared, so the square root of 2 squared, which brings us 2, plus 1.6 squared, which brings us almost 3, and then take the square root out of it, and it all brings us a length of 2.12. We can also calculate this angle, which is the arctangent of the vertical part divided by the horizontal part. So the arctangent, or the tangent inverse of 1.6, which is the vertical part, divided by the horizontal part, which is square root of 2, and then we get 48.3 degrees, which equals 0.843 radians. Well, that's the combined vector. So that is the current which flows into that resistor. Well, we have seen in several videos before that we have so-called voltage current relationships for the most used passive components in electronic circuits, which are the resistor, the capacitor, and the inductor. For a resistor, it's quite easy. U equals I times R, which is Ohm's law. For the capacitor, we have seen that the current is equal to C times du dt, or it's equal to C times the derivative of the voltage. For the inductor voltage is equal to L, which is the inductor value, times the IDT, which is the derivative of the current. Well, we know these relationships. Let's figure out what this means for phasors. First of all, the resistor. We have seen U is I times R. Suppose I is a sine current with an amplitude of I top, so call it I top, a angular frequency of omega, and a phase value of phi. Then U is I times R is the top value of the current times R times the sine of omega t plus phi. What we see is that this U vector, this voltage vector, has of course a different amplitude. Here it was I top, and here it's I top times R, but not only the frequency stays the same, but also the phase angle stays the same. And that is of course what we expected when using a resistor. Well, We can draw it in a time domain. Suppose the black curve is the current and the green curve is the voltage. Of course, they have a different amplitude, but we see that the frequency is the same, but even more important, the phase angle is the same. So in a phasor diagram, when we put the current vector over here, then we see that the voltage vector is at the same axis, but of course it has a different length because the amplitude is the top value of I times R. That's for a resistor. Now let's look to the inductor, and from the inductor we have learned that U is L times the I dt, or L is the derivative of the current. Suppose again that I is I top times the sine of omega t plus phi. Now we can calculate U by taking L times the derivative of that current. So L times derivative of that current, well, I put the complete current expression over here, and then we get L times the derivative of that current expression over here. How do we come to the solution? Well, the top value of the current is a constant value. We can put that in front of the derivative. We can put it over here. The derivative of a sine is a cosine, which is standing over here. And then we have to use the chain rule and take the derivative of omega times t, which brings us an omega. And then we have u is the top value of I times omega times L times the cosine of omega t plus phi. Well, we can first of all draw a time domain a plot in which again the black curve is the current and the green curve is the voltage. And we see that the voltage leads the current, and that is of course because the voltage is a cosine and the current is a sine, and the cosine has a top earlier than the sine, so the voltage leads the current. That is what we expect from an inductor, and that is what we see. So let's put that information in the phasor diagram. We put the current over here, and we have to define the voltage 90 degrees or pi over 2 in front of the current, so it has to lead the current, so the voltage can be put over here. For simplifying reasons, we have given it the same length, but that might also, it doesn't have to be the case because the voltage amplitude is the current amplitude times omega times L, which could be by incidence the same, but most of the times it's not the same, and then this length difference. But what is the important factor is that the voltage leads the current, so this angle is plus 90 degrees. Now let's look to the capacitor. For the capacitor, we know that I is C times du dt. And when I is I top times sine of omega times t plus phi, we can define U by solving this equation. We can say I over C is du dt, and U is the integral of I over C towards the time. So then we get U is 1 over C times the integral of the complete current expression, which is over here. Well, let's work that out. We can bring this amplitude for the current in front of the integration, put it over here. 1 over C is over here. And because of the chain rule, we have to imply it the inverse way. So we have to do get the 1 over omega up front over here, because when we take the derivative of this voltage expression, we could get the current, and by using the chain rule, we get an omega over here, which has to be put away by the omega over here, because in that current there is no omega. So this is my expression for the voltage across that capacitor when this is the current relationship for that current through that capacitor. Well, let's work it out in a time domain plot. And again, the black curve is the current and the green curve is the voltage. What we see is when this is the current, that when the current is a sine wave, the voltage is minus a cosine. Well, a cosine should start over here, minus the cosine starts over here. So what we see is that the current, which is the black spot, leads the voltage for a capacitor, and that is what we expected. It leads it by 90 degrees. Well, with this information, we can put it in a phasor diagram. We have the current over here. We see that the current leads the voltage, so the voltage has to be 90 degrees, an angle of 90 degrees lagging the current, so it has to be over here. Well, this is 90 degrees, so this is the voltage factor. But of course, this amplitude doesn't have to be the same as the current factor. Well, this is the relationship for the capacitor. So what you have to know is when we have to add AC signals with a different phase value to each other, you have to split up the vector by a horizontal part and a vertical part, and add up these horizontal parts and these vertical parts, and then get a resulting vector. So this is a horizontal part for this vector, and this is the vertical part. Let's do this in an example in which we have a current source over here, and the current source is defined by I is I top times the sine of omega t. So the phase angle of this current is 0, and this current flows through a series connection of a resistor and an inductor. And what we want to know is the voltage UR. We want to know the voltage UL, so across the resistor and the inductor, and we want to know the total voltage over resistor and inductor. And we know because both resistor and inductor have a different voltage current relationship, we may not add the numbers together, but we have to do it with vectors. Suppose this is my current waveform. It's 2 times the sine of 628 times t, and we know that the top value of the current is 2 amps, and omega is 628 radians per second. R is 20 ohms in this example, and L is 10 millihenry or 0.01 Henry. Well, first of all, we can calculate when we have drawn the current over here, because the phase angle is 0, we can calculate UR, and UR is I times R. So it is at the same axis as the current, because the phase shift between current and voltage for a resistor is 0. So this is UR. Now we can calculate UL, and UL is equal to L times di dt, which is L times this times 0.01 times di dt, the derivative of the current over here. And it will be projected on the vertical axis over here. And now we can add these vectors together. We do it this way, and then we get UB, which has an amplitude of UR squared plus UL squared, and taking the root out of it. And we can also calculate the phase angle, which the phase angle of UB to the horizontal axis, which is UL over UR, and then the inverse tangent of this angle. Right, that's all about phasors. Thank you very much, and I see you next time.